Alright, we're live. So we are continuing our logarithm stuff. It should be a really short lesson today. We'll finish all of our logarithm stuff and then go back over our projectile motion stuff from last week. So our objectives are to rewrite the logarithms according to their properties of logarithms, and use the properties of logarithms to derive functions we couldn't derive otherwise, mostly just using the power property of logarithms so that we can derive functions raised to the power of a function. Okay, so from last time, we had a bunch of logarithm rules that you guys learned in your packet for homework. So I'm going to be focusing mostly on the last three, so properties of logarithms, and the definition of logarithm here. Using our definition of a logarithm, if I had log base a of a, then I could rewrite that as a2 something equals a. Since a by itself is a to the first power, so I could say this. Log base a of b equals c if a to the c power equals b. So after rewriting this in exponential form, I would get whatever this question mark was should be equal to 1. So if I have log base a number and I'm taking the log of the same number, I'll end up with 1. Log base a of a is 1. Okay, another cool rule. If I have log base a of 1 equals something, and I rewrite that in exponential form, this would be a to the something equals 1. Any real number raised to the 0 power should give me 1, so this question mark should be 0. So that gives me another new rule, log base a of 1 equals 0. Doesn't matter what your base is, if you take a log of any base of 1, you'll get 0. And then if I try to take a log of any base of 0, and I rewrite that in exponential form, I get a to some power equals 0. There's actually no number that I could raise a to in order to get 0. If this had been 4 raised to the negative 1 power, I would get 1/4, since that just lets me move this to the bottom of a fraction. So there's no way that I could get 0 or a negative number. Therefore, the log base a of 0 does not exist. So that gives us 3 more rules using our definition of a logarithm. Okay, then I'm going to look at, this is the format that you guys will have for the homework for today's lesson. So because it's a little bit weird, I'm giving you 3 variables, r, s, and t here. And what they'll be equal to in terms of log base 7. So if I had log base 7 of 8, that would be r, log base 7 of 10 would be s, log base 7 of 12 would be t. And I want to know what log base 7 of 56 would be. So what I'm supposed to do here is to break this apart. So 56 is 8 times 7. So I've got log base 7 of 8 times 7. If I'm multiplying numbers inside the logarithm, then I can expand this with my product property. So with this property, if I'm multiplying inside the same logarithm, I can break that apart into 2 logarithms of the same base. This would be log base 7 of 8 plus log base 7 of 7. Log base 7 of 8 we said is r, so I can substitute r here. Log base 7 of 7, if I have the same number on the base that I'm taking the logarithm of, then that's 1. So I have r plus 1 or a. Okay, slightly trickier one, same format. If I have log base 7 of 150, that would be 150 is 10 times 15, or 2 times 5 times 3 times 5. So this 2 and 5 are already 10 can group together, since I've got log base 10, or log base 7 of 10 is s. But this 3 and 5 don't match with anything we've got. So I'm going to see if I can match them. 3 times 4 would give me 12, so I'm going to multiply 4 on top and on bottom so that I don't change anything. So now this 3 and this 4 would give me 12. And then 5 times 2 would give me 10, so this 5 times 2 would give me another 10. Okay, on bottom I've got a 2 times 4, which is 8. Okay, so if I group this together, this will be log base 10, so here's 110, plus log base 7 of 10, so I've got, here's another 10, log base 7 of 12 is a 3 times 4, and then on bottom, with our quotient property, if I am dividing, then I can expand that by subtracting. So with this property, dividing by 8 is the same thing as subtracting log base a of 8. So that'll give me minus log base 7 of 8. And now I can substitute. Log base 7 of 10 is s, plus log base 7 of 10 is another s, so that's s plus s is 2s, plus log base 7 of 12 is t, minus log base 7 of 8 is r. Okay, any questions on what we did here? Turn you guys up, going once, any questions? Okay, you guys are really quiet. I'm going to take that as no. So we've got the 3 new rules that we just created using our definition of a logarithm and our properties of logarithms and definition of a logarithm all in one slide if you need it later. If I was going to derive any logarithms with other bases, so we've seen the derivative of ln x. So if y equals ln x, y prime would equal 1 over x. If I wanted to derive any other base though, then I could rewrite this with change of base formula. So change of base formula says I can rewrite this as log base whatever you want of what our number was, divided by log base whatever you want of our base of the original logarithm. So log base 2 of x is the same as ln x over ln 2. 1 over ln 2 is just a constant, so now I can derive this normally with our rule for natural log. So if I derive natural log x, I get 1 over x, and my constant in front will stay the same. Okay, so that gives us our new rule. If I had a log base a of x, the same process would happen, only my 2's would be a's, which would give me 1 over x times ln a. Okay, and one more thing we can do. If I wanted to use logarithms to help me derive functions, if I had a function raised to a function, we don't have a rule that will allow us to derive this. On some of your formula sheets, you did see if I derive a to the x, I'll get a to the x ln a, which we'll prove in a second. But this a has to be a real number for this formula to work. So if I had a function instead, like x raised to the 3x, in order to break that apart, what we could do is we could take a natural log of both sides. That allows us to use the power property of logarithms to pull this 3x out. So first I've got product property, I can break these apart, and then power property, I can pull that 3x out. And now if I derive the left side, I'll get 1 over y dy. So on the right side, if I derive, this natural log 2 is a constant, will go away, and then this is product rule, 3x times ln x will give me 3 ln x plus 3x times 1 over x. I can multiply both sides by y, and I'll get the slope. And that dy over dx is what I was looking for, derivative of the original problem. If I wanted to, I could resub in, because we know our original y is really 2x, 3x, and that would give us this. That's black. Dy over dx is equal to 2x to the 3x power, that's what we had originally, times everything else that we had here. So that's 3 ln x plus 3. Any questions on what we did here? Nope. Okay. Last one then, same idea. So if I wanted to derive a to the x, I'm going to start by taking a natural log of both sides. That allows me to use my properties of logarithms to break this apart. Then I can pull the x out with my power property of logarithms and derive both sides normally, now that these are just natural logs. So if I derive this normally, on this side, if I derive natural log of x, I get 1 over x, and then with chain rule I would multiply by x prime, right? So if I derive natural log of y, I would get 1 over y times y prime. If I derive x times ln a is just a constant, so if I derive a constant times x, I would just get the constant. Okay, then I can multiply both sides by y. Since y is a to the x, I can substitute. So instead of y, I'll replace that with the original y, which was a to the x, and I've got my final answer. If I derive a to the x, I will get a to the x ln a. So that gives us two new derivative rules. If I derive a to the x, I get a to the x ln a. If I derive log base a of x, I'll get 1 over x ln a. Any questions on this one?
No.
Nope. Okay. So I've got two more slides, mostly just for you guys later. So if you need it, all of our derivative rules so far with logarithms and trig functions. I guess I'll discard those for now. And then our previous slide has all of the logarithm rules if you need it. Okay, so I'm going to jump back and we'll look at our projectile motion stuff from previously.
Mr. Brandon,
Yes.
may you send this as a PDF because when I open it on my doc, the words overlap.
Okay. Let me do that now before I forget.
Okay, thank you.
Okay, so I'm going to send off the answers through WeChat and Skype coming up here in a minute for Kenichi. For the homework, it's also available on WeChat and Skype under the rewriting logarithms classwork file. Okay. And then, as I said, I'm going to keep going through the projectile motion stuff. We're technically done with the class right now. So if you don't have any questions on the projectile stuff, you're welcome to leave. If you want to stick around, you can. However, we do have a test coming up. So we're going to have our last live lesson Friday before the test for our review. Test covers projectile motion and logarithms, compound interest, and continuous compound interest. Continuous compound interest is what we'll talk about on Wednesday, and then we'll review everything on Friday. The test will be due on Tuesday at 9 a.m., so it'll give you guys 4 days to complete the test. I am trying to write 17 different forms of the test right now. So assuming that all works out, then we'll all have slightly different forms of the same test. But it's taking quite a while. Okay. So starting with our first one, we had Nikita launching at 30 degrees above the horizontal at 15 meters per second, starting 30 meters above the ground. We want to know his maximum height. So in order to get that maximum height, I'm first going to break this apart into his vertical and horizontal components. So we've got our picture that looks something like this. He was launched at 15 meters per second at a 30-degree angle, so there should be a Vx and a Vy that we can solve for. So we break those apart using sine and cosine. And then I can throw those into our horizontal and vertical distance formulas to get the two formulas we need. So to get maximum height, I need to derive my vertical distance equation and set that equal to 0. Because when he doesn't have any vertical velocity for for Nikita himself, then he stopped going up and started to go down. In order to change direction, we have to hit 0. So if I derive this, I'll get negative 9.8 plus 7.5. Sine 30 is 1/2, so 1/2 times 15, 7.5. So that equal to 0, and solve for t is 7.5 over 9.8. And then to find the height, I can take that time and plug that back into my height equation to get 32.87 meters. Any questions on part 1?
Wait,
No.
I got 36.136 something because the converting the time, it's like 0.8, like making it to decimal.
So there were a couple of rounding errors, and there were some really common rounding errors from a couple of people that cut off some decimal points at different points. So if your problem was just a rounding error, I'll still give you full credit. So if you wrote something like 32.6, you should get full credit for that. Okay. If you're within about 2%, I'm going to give it to you regardless. And then if you're not within 2%, I'm going to go back and see if I can find a rounding error. If I still can't find it, then I'll have to mark it wrong. But okay, so for number 2, when Nikita hits the ground, and how far away will he land? So to figure out when he's hit the ground, he will hit the ground when his height is 0. So I'm going to start there. Set his height equal to 0 and solve for t. I chose to use the quadratic formula this time. You could choose to complete a square or a graph, and either way would work. But either way, I should end up with 2 different times, one of which is negative, and so that doesn't make sense. So I've got my time as 3.355 seconds. Now, again, whatever you chose to cut off your time here is going to affect your final answer for your distance in your next part. I stored this in a calculator and did not round when I came back into this next part. However, if you did round, you'll be slightly off, but it should be pretty close. So I'm going to take this time, plug it into my horizontal distance equation. That should give us how far away in meters we are before we hit the ground. Any questions on that one? Okay. For number 3, I want to know his velocity vector exactly 1 second after he leaves the ramp. Now, originally, I had just asked for the what the speed would be exactly 1 second, so total speed. I did go back last minute and change this to velocity vector, so do have this kind of added over on the side here for the angle, since our velocity needs to have both a magnitude and an angle. So to get the magnitude, I'm going to solve for what his exact horizontal velocity would be and vertical velocity would be at the time that we want. So this is the time, which is 1 second after he leaves the ramp. So to get the vertical velocity at any time, I could derive the vertical displacement, and that would give me this equation, negative 9.8t plus 7.5. And then the horizontal velocity actually doesn't change, so we don't have any, gravity doesn't affect us left or right, and we don't have any crazy air wind currents or air resistance in this problem, so the horizontal velocity is going to stay the same at 15 cosine 30. So I can take those two and plug that into Pythagorean's theorem. So at any point, so in this case 1 second after he leaves, would look something like this. So he's actually already started to drop at that point. So we've got some velocity horizontally, some velocity vertically, and then a total velocity and an angle. So I could use Pythagorean's theorem with Vx and Vy to get V. That'll give me the magnitude of the velocity, which is around 13.2-ish. And then to get the angle, I'm going to zoom in here. So to get the angle, I use tangent. So here's my picture again. Vx, Vy, V, and theta. So I use tangent would be opposite over adjacent, and that gave me my angle. Now that negative is just telling us the direction. Right now we are below the horizontal. So that gives us about 10 degrees below the horizontal. If you wrote negative 10, I'll take it. Any questions on part 3? Okay. Then 4 for slope of the arc. His change in y over change in time over change in x over change in time would allow my change in times to cancel, giving me change in y over change in x would give me the slope of his trajectory or the slope of the arc. So this is after Nikita jumps. If I was going to look at a 2D picture, y in terms of x. So where this is height in meters, and this is distance away from the launch point in meters. This would tell me the slope of his trajectory. So this slope at this point would be dy over dx, rise over run. Okay, then that slope. In order to get it, I would need dy over dt, which is y prime t, and dx over dt, which is just vxt. So I can go back and plug in our times again. So at 1, we already solved for in our previous part for both x and y. I'm going to zoom out again. So y prime at 1 was 2.3. And x prime at 1 was about 13. So my change in y over change in x should be negative 2.3 over 13, or negative 0.177, which is the slope of the arc.
Mr. Brandon, so
Yes.
13 is fine.
13 is fine, yes.
Okay.
Again, so as long as you're within 2%, I'm going to give it to you automatically. If you're not within 2%, then I'm going to go back through your work and see if I can find a rounding error. If I do find a rounding error and your process is right, then you still get it right. I know Desmos cuts off some of these automatically too. So if you use Desmos, then some of you had some regular wrong answers, and that's what happened, I think. Okay, for the next one, we should probably go up to the problem first. We kicked a ball at 40 miles per hour from the ground, and then we stood 30 feet away, or her friend stood 30 feet away and tried to headbutt the ball into the goal when it dropped to 5 feet high. So I've got one person that's kicking it up to another person that's going to then kick it into the goal, or headbutt it into the goal in this case. So in order to headbutt, we have to be 5 feet high. Okay, so the first thing we need to do is I need to convert because we're in miles per hour and feet, so we're not in the same units. So I'm going to convert in order to get into feet per second. So there are 5,280 feet in 1 mile, and then 3,600 seconds in 1 hour. So if we split that up, that gives me 176 over 3 feet per second. Again, if you wrote this as a decimal and rounded, that does change all of your answers for the entire problem, which is okay. I will take that that rounding error and carry it through, so you should still get everything right as long as your process is right. Okay, so the first one, I want initial vertical velocity and initial horizontal velocity. So for horizontal velocity, I can take the cosine of our angle, which we don't know yet. So if you stopped here at this part, I will still give you full credit for part 1 as long as you solved your angle down here, since you've got everything you would need to get the right answer. And then same thing for your vertical velocity. However, if you did come back and plug in your angle, this answer would either be this, or it would be based off of your higher angle, and then your velocity would change, would become these two. Okay, we did end up with 2 angles. The reason why is because she could have kicked the ball, Jenny could have kicked the ball to Sarah at a high angle, and then it would have been longer in the air in order to reach the same point. Or she could have kicked the ball at a low angle, and it would have taken a shorter time in the air to reach the same point. There are 2 angles that worked. In order to solve for that angle, we can take our height equation. If I've got our height equation and we're starting at, so I'm starting from the ground and I want to be at 5 meters. So that means this 5 will go over here, means I want her total vertical velocity to be equal to 5. So I moved that 5 over to the opposite side to subtract it and set everything equal to 0. That way I can factor and solve for t. Now, I did not expect you to do this by hand. However, if you did, you could have tried to complete a square and then solve that way with a calculator. I don't expect you to do that. What I want you guys to do is to plug this into a graphing calculator, so either Desmos or a real graphing calculator, and calculate your intersects with 0, or do it up here and calculate your intersects with 5. And that should give you 2 different answers for your time. Only one of them should make sense. So then we're gonna take that time and plug it in to get our 2 angles. Any questions on what we did? Okay. Do this again. I've got 2 equations here, horizontal and vertical velocity, and I've got 2 different variables. So you can solve this with the systems of equations. Solving for one variable, substituting solving for the other variable, at which point you need a graphing calculator in order to plug it in and calculate your intersects. Okay, for part 3, I'm looking for the actual speed at the instant when Sarah hits it towards the goal. So I'm looking for the exact speed at this specific time, the time when Sarah would be able to headbutt the ball. So if I want to get that exact speed, I need to look at the derivatives of our displacement equations, so both horizontally and vertically. So if I derive her vertical displacement equation, I'll get this, negative 32t plus 176 over 3 sine theta. And then her derivative of the horizontal displacement is still vxt, hasn't changed because there is no air resistance, there is no wind. Gravity doesn't affect us left or right, only up or down. So I can use Pythagorean's theorem again to figure out what the total magnitude of her velocity would be at that point. And once I have done Pythagorean's theorem, we can figure out, just actual speed, so we don't need an angle, since speed is scalar. So we just need that magnitude. Okay, now we do have our time. However, your answer will change here for the speed of the, your process for your answer will change here for your speed of the ball. For which angle and time you'll end up plugging in, since your angle will be different, either 17.7 or 81.6. However, your final answer will end up being the same for the total speed, regardless of whether you kicked low or kicked high. So what that means is, if you kicked the ball low, then you're going to have a lot more horizontal speed than you have vertical speed, but your total actual speed once she hits the ball will be the same as if you kicked the ball high. Kind of cool. Any questions on 3? Okay then, number 4. Create an equation that models the ball's trajectory. So that's y in terms of x. So what I'm going to do is I'm going to take our time, since I've got a time equation, and I also have a vertical displacement equation that is both an angle and a time. So I can substitute for all of my times and get one equation that has angles. And that gives me an equation for the vertical velocity. Now, I left it there in my answer key because, again, there are 2 different angles. However, if you plug that in, you can get a general equation with just decimals here.
Mr. Brendan,
Yes.
like, I didn't keep the, I didn't keep the, like, I didn't keep it as a fraction form, but like, I came out like, I multiply everything together, and there's like numbers on the top and numbers on the back.
That's okay.
On
So
the bottom.
all that means is you did have an angle for theta that you plugged in. So you got
Yes.
that as a decimal for your final answer, and you use this instead of a fraction, you use that decimal that you got originally. So that's okay. Your answer will be rounded twice over, actually, because I'm assuming you rounded the angle and that you rounded the fraction.
Oh,
But that's okay. So you should still get full credit for that. Again, in my answer key, I just left this as an angle
hopefully.
because I've got 2 different angles that you could have provided for your answer, but I will take the answers for either of those angles.
Okay.
Okay, any other questions on the first one? Sorry, second problem. Okay, and last one for today. So we had Abby on the moon, where the acceleration due to gravity has changed, is no longer 9.8. She is jumping at a 30-degree angle and lands 21 meters away. I wanted to start out by writing equations for horizontal speed, initial vertical speed, and initial actual speed. So her horizontal speed, which doesn't change at all throughout the jump, would be her distance times time. Would be her velocity vector times the cosine of her angle. If I wanted to get the horizontal distance, it would be her horizontal speed times time, which I could set equal to 21 meters, since we know she lands 21 meters away. When she lands, her height will be 0. So I can set her height equation equal to 0, and that also gives me an equation with a t in it. So now I've got a t and a v, a t and a v. So I've got two equations and two variables. So we can use a system of equations in order to solve that. So I'm going to use our first equation here.